You ever wonder why your computer can do some things in like the blink of an eye, but then it just grinds to a total halt on others? Well, it's not random. There's actually a deep and pretty fascinating reason for it. Almost like a map that charts the entire territory of what's computationally easy and what's fundamentally hard. Today, we're going to explore that map. Okay, let's just dive right in with an example. A computer can sort, say, a million names almost instantly, no sweat. But then you ask it to find the absolute shortest route for a trip through just 15 cities, a classic problem, by the way, called the traveling salesman problem. And that same computer could take days, maybe even years. So, what is the fundamental difference here? Why is one so easy and the other a total nightmare? To answer that, we can't just go with our gut feeling. We need a formal way to measure a problem's difficulty. And that brings us to this amazing field called computational complexity theory. It's all about creating a really rigorous framework for understanding what hard actually means when we're talking about computers. Yeah, you can think of this theory as being like cartography, but for computation. We're drawing a map. And it doesn't just look at one specific program on one specific computer, but at the inherent difficulty of the problem itself across all possible algorithms that could ever exist to solve it. It's really about charting the very limits of what's practically possible. So how do we measure this time? We don't use a stopwatch, right? I mean, that would totally depend on how fast your computer is. Instead, we count the number of basic steps or operations an algorithm takes to get to the finish line. We're really interested in how this number of steps grows as the size of the problem, which we just call n, gets bigger and bigger. And a lot of the time, this step count can be described by a mathematical formula. So for a problem of size n, the total number of steps might look something like this function right here. It tells us exactly how the amount of work scales up as the input gets larger. But here's the thing. When n gets really, really large, like a million, that n squared term becomes so massive that the other parts, the 15n and the 40, they're basically just noise. They're a drop in the ocean. So computer scientists use what's called big O notation to focus only on the part that grows the fastest, the dominant term. We just say this algorithm is O of n squared, or order n squared. And this brings us to the great divide in the world of computation. On one side, you have problems that can be solved in what we call polynomial time, like n squared or n cubed. We consider these tractable, or, feasible. But on the other side, you have problems that require exponential time, like 2 to the n. These are intractable. The number of steps just explodes so quickly that even for pretty small inputs, they become practically impossible to solve. And now we arrive at the most famous part of our map, this great, unsolved mystery right at the heart of computer science, a vast, kind of foggy region known as the P versus NP problem. All right, so first we have the class of problems we call P. These are the easy ones, the tractable ones we just talked about. P stands for polynomial time. Basically, if a problem is in P, it means we have an algorithm that can find a solution for it efficiently. Sorting a list, that's a perfect example of a problem in P. Then we have the class NP. Now, this is the set of problems where if somebody just gives you a potential solution, you can check if it's correct really fast, in polynomial time. The classic example is a Sudoku puzzle. Solving it can be incredibly hard. But if I hand you a completed grid, you can verify that it follows all the rules almost instantly. The solving is hard, but the checking is easy. So here's the crucial point, the relationship between them. Every single problem that's easy to solve, that's in P, is also easy to verify. It's in NP. I mean, that just makes sense, right? If you can find the answer quickly yourself, you can definitely check it quickly. This means that the entire class P sits inside the bigger class NP. And this relationship leads us to the single biggest, most profound, unanswered question in all of theoretical computer science. Are these two classes of problems actually the same thing? Is every problem whose solution can be checked quickly also a problem that can be solved quickly? In other words, does P equal NP? This question is so ridiculously important that the Clay Mathematics Institute has a $1 million prize just waiting for a proof. I mean, a solution either way would have absolutely world-changing implications for everything, from medicine and logistics to all of modern cryptography. Okay, let's bring all this down from the clouds of pure theory and see how these ideas work in the real world. To really get a feel for how we navigate this hard NP territory, we're going to tackle a classic problem. one that puts you right in the shoes of a very, very calculating thief. This is the 0-1 knapsack problem. So, picture this. You're a burglar with a knapsack, and it can only hold a certain amount of weight. You're standing in a room full of treasure. Each item has its own weight and its own value. Your goal is to fill your knapsack to get the absolute maximum value, but without going over the weight limit. What do you take? So how would you even solve this? Well, the most obvious way is to just try every single combination of items. But if you have n items, there are 2 to the n possible combinations. And as we just saw, that exponential growth makes this problem completely intractable. For just 60 items, the number of combinations you'd have to check is greater than the number of atoms on Earth. So yeah, not gonna happen. So brute force is out, but there's a really powerful technique, a clever trick that can find a path through this seemingly impossible landscape. It's called dynamic programming, and the key idea is to be smart by remembering what you've already figured out. Now, you've probably heard of divide and conquer, where you break a big problem into smaller, independent pieces. Dynamic programming is different. It really shines when the smaller problems are not independent, when they overlap. Instead of solving the same little subproblem over and over again, dynamic programming solves it just once and then stores the answer in a table to use later. No repeated work. The approach itself is super methodical. First, you figure out how a big optimal solution is built from smaller optimal solutions. Then you write down a rule for that. And finally, you build a table and you just fill it up from the bottom, starting with the easiest cases until you get all the way to your final answer. For our knapsack problem, this looks like a big grid. Each row represents one of the items we could decide to take, and each column represents a different possible weight limit for our knapsack. We fill in each little box by making a simple choice. Are we better off including the current item or not? And we base that choice on the best answers we've already calculated for smaller knapsacks. And here's the magic. By building this table, which has a size of n by w, where w is our weight limit, we solve the problem. The runtime is just proportional to the size of that table, ONW. We've taken an exponential, intractable nightmare, and with this one clever trick, we've turned it into a polynomial time, totally tractable solution. Amazing! Okay, let's zoom back out. We've gone from the really high-level theory as P versus NP, all the way down to a hands-on technique for cracking a tough problem. So why is having this map of complexity so incredibly important? It's because this map is our guide. It tells us when a problem is likely easy, so we know we can go hunt for a fast algorithm. But maybe even more importantly, it warns us when a problem is probably intractable. It saves us from wasting years of our lives searching for a fast solution that probably doesn't even exist. It pushes us to either find a good enough approximation or to find a clever technique, like dynamic programming, that can chart a special path right through that hard terrain. You see, understanding complexity gives us a map of the digital universe and its fundamental limits. It's our guide to what is even possible. And the biggest question it leaves us with is this. Now that we have this map, what new problems will we solve? And what completely new frontiers are we going to discover?